In this lecture, we're going to talk about predicates. A predicate is a function. It's written p of x, and it takes in some input. So x is replaced with some sort of input. We'll talk about that in a second. And then the output is either true or false. Now you might say, we don't know what a function is yet. We haven't done that in class, and that's true. But it's not important for right now. A predicate is, think of a predicate as something that takes an input from some domain and it produces an output that is either true or false. So for example, I could write p of x as x is greater than 2. Okay? Now, what is p of 5? Well, is 5 greater than 2? Yes, so p of 5 is true. And how about p of 1? Well, is 1 greater than 2? No. That's false. How about p of x equals x squared is greater than 0? Well, p of 1, p of 2, it depends on what the domain is, but p of 0.5, these are all true. What's p of 0? Is 0 squared greater than 0? No, so p of 0 is false. We could also have, we don't necessarily need to work with numbers. For example, p of x could be banks are closed on x. Okay, so p of Saturday would be true. P of, well, let's say Monday, assuming that Monday is not a holiday, would be false. So given a particular predicate, p of x, we're going to be interested in what values of x make p of x true and what values of x make p of x false. So another way of writing this is, we'll be interested in questions of the form, does there exist an x such that p of x is true? This is often written, there exists x, p of x. We want to know, is this true or false? Another question that we'll be looking at is it the case that for every x, p of x is true? Sometimes this is written for all x, p of x. Now the key question here is, where is x coming from? And so with oftentimes we'll specify a domain for a predicate. And the domain, well, this is the set where x might come from. So for example, if p of x is the predicate x is even, okay, let's say the domain is all positive integers, then yes, there does exist an x such that p of x is true. So there exists p of x. Yeah, this is true. Why? Well, p of 2 is true. But what if the domain, instead of all positive integers, we said was all odd integers? Okay. Then there exists p of x? Well, that would be false, because we've switched from the domain being all positive integers to all odd integers. Okay, what if we switched it again and said, instead of all odd integers, we'll do all even integers? Okay, well then, there exists p of x is clearly true. I mean, the domain is now all even integers, so for every x, p of x is true. And so if the domain is all even integers, then for all x, p of x is true. So the domain is very important, when you're trying to figure out, well, does there exist an x such that p of x is true? Is it the case that for all of x, p of x is true? You need to specify a domain. If, for example, if our domain to p of x were days of the week, then it wouldn't even make sense. I mean, the truth value of p of x would be undefined. So let's say I have a predicate, p of x. Remember that as soon as I write there exists an x, p of x, this predicate here, this was a function. It took some input and it output true or false. Now I've written there exists an x, p of x. This has a value. It's either true or it's false. If there's an x that makes p of x true, and we've specified the domain, then it's true. If for every element in the domain p of x is false, then this statement is false. So there exists x, p of x is either true or false. Similarly, when I write for all x, p of x, this is now either true or false. As soon as you add these quantifiers in front of the predicates, you change it from a predicate itself, you change it to something that is just either true or false. Okay, so let's assume that I have written p of x, or let's write p of x as x is even. And let's write another predicate, q of x, where x is odd. And let's say the domain is positive integers. Okay, so how about the following? There exists an x, p of x. Okay, this is true. Right? For example, p of 4. How about there exists an x, q of x? This is also true. P of 3. What about there exists an x, p of x, and there exists an x, q of x? Well, this is true. There exists an x, p of x is true, and there exists x, q of x is true. And as we saw last time when we were dealing with Boolean formulas, true and true is true, so this is true. But how about this? There exists an x such that p of x and q of x. Is this true? No, this is false. Why? Is there a positive integer that is even and odd? No. So be careful here. You can't always distribute the existential quantifier. You might think, oh, I can distribute this existential quantifier and get there exists x p of x and there exists x q of x. You might think, oh, this is sort of logically equivalent to this statement, but that would be false.